Sorry, so loud.
Time. All right. Good morning, everyone. Hopefully everybody can hear me. Welcome back to the first class, second week. As a reminder, we have already done a very brief review of a couple of topics that will be relevant. Some of them were already relevant, not irrelevant, relevant, and many will continue to be relevant. We will bring up a couple of review topics as they become necessary throughout the semester as well, but again, not covered in great grand detail. If you need more practice, we should all know by now that you can go to the prereq material in the Canvas course, as well as that prereq homework in the My Math Lab homework. And remember, if you get an 85 or higher before the first test due date, then I'll give you a 5-point bonus on the first test. That's an excellent reason to, de-rust, basically. We also covered 1.1 very briefly, just how do you graph, what are coordinates, how do they work, how can we graph an equation using a very generic and ultimately not that great of a method. We'll learn better methods in here, but for now, this is what we got. Talking about intercepts, we emphasized how important it is to know which one's the x-intercept and which one's the y-intercept, because they both have ramifications throughout this course. X-intercepts will be used in great grand detail for graphing quite often, as we'll see. Y-intercepts are very nice to have. We still use them, but the x-intercepts, we can talk about a lot more features with them for reasons that'll become clear later. And then we started our journey into 1.2 on linear and rational equations. We gave the basic 4 steps to solve any of these equations. We mentioned that the order of these 4 steps is arbitrary. This is generally kind of the best approach. Steps 1 and 2 are pretty easy to swap with practice. Step 4 really should be the last thing. Step 2 is arguably optional. You can solve linear equations without doing step 2 most of the time, but it will make them much more difficult because then you'll have to put up with those decimals or fractions along the way. We did a couple examples, and we will go right into a third example. And this example is going to be similar to B, but different, as we will see. So x plus 2 over 4 minus x minus 1 over 3 equals 2. Just kind of separate that. All right, so here is another equation. We know it's an equation because it has an equal sign in it. And it's got fractions. We know it's got fractions because we see a top and a bottom on at least one thing. So because we have an equation with fractions, remember if this was a plus sign, it wouldn't be in an equation, and the steps above, that step 2 where we can get rid of the fractions, would not be relevant. So that's not a blue plus sign. Let's get rid of it. There we go. So here's our equation. And we're going to, again, follow these 4 steps. But remember, you don't have to necessarily do them in this order, although it's a great order. And a lot of the times when you do step 2, step 1 ends up poking its head up. Spoiler alert. So distribute or combine like terms. There's nothing to distribute. There's no like terms to combine. Asterisks. Actually, you could argue you could distribute this negative if you wanted, but I'm going to hold off on that. Again, you could, and if you can handle it that way, be my guest, as long as you can do it correctly. Because I find a lot of people really mess up distributing this negative, but it's going to show up either way at some point. So just know that minus will be an issue. So for now, we're saying nothing to distribute or like terms to combine, even though there arguably are. So step 2, if there's fractions, multiply all terms by the LCD. So we got a denominator of 4, we got a denominator of 3, which means our LCD is 12. Remember, if you're rusty with finding your LCDs, you've got to practice being able to do that. So we're going to take each of these bits and multiply them by 12. Now, I'm not multiplying the 12s in the bottom. With fractions, the 12 goes in the top. And there's one fraction here, there's a second fraction here, and then a whole number. Those are the things that are getting multiplied by the 12. So this x plus 2 over 4 minus, I'm going to leave some space, x minus 1 over 3 equals, leave some space, 2. So we're taking the 12 times this fraction, the 12 times this fraction, and the 12 times this 2. Again, the basic idea here is I've multiplied both sides by 12. Whatever I do to one side, I do to the other, not breaking any rules of algebra. Now, let's go back to problem B for a hot second. And when we found our LCD, which was coincidentally also at 12, we multiplied by every single fraction, every single whole bit, all the different pieces. We said here that while you can multiply the top first and then divide, it's easier if you reduce first. That's how you make things easier. It's easier here because it keeps the numbers more manageable, but it's more important in this example because the tops have got multiple terms. So the tops are a little more complicated. So if you were going to take this 12 and multiply it out, you'd have to give it to the x and the 2, and that might throw you off for when you got to reduce by the 4 here, or by the 3 over here. You may only reduce it in one of the top parts when you actually are supposed to reduce it in both of them. So here is my, again, hint that you should reduce first. Now I'm not going to say it's mandatory, but it feels like it's more required. So I'm going to do this little double arrow thing saying, hey, this goes over here next. So by reduce, I mean we're going to take the 4 and the 12 and reduce them. So this 4 would go into this 12 3 times. Now I can't reduce the 4 and the 2 like that because this 2 is part of an addition or subtraction in the top. This 12 isn't being added or subtracted, so these can reduce with each other, but these cannot unless the x also had a 2. So 4 goes into 12 3 times. Let me go ahead and write that. So now it's going to be 3. You still have the x plus 2 from the top of the fraction. The bottom is now a 1. See, the bottom is now a 1 when this is a 3. I'm going to erase that in a second. So we don't need to write the bottom, but look at how weird this looks. 3 and then x plus 2. This looks like you're just taking the 3 times the x, and you're not. You have to, wrong color, you have to introduce a parentheses when you're doing it this way. When I say 4 goes into 12 3 times, that 3 needs to multiply by the entire top. To make sure that happens, you give it a parentheses like so. You'll have to do the same thing for the second one. So you'll say 3 would go into 12 4 times, and of course the 3 is now a 1 and it's gone. There's still this minus out front, so this is like a minus 4 that's multiplying the x and the minus 1. So again, parentheses are going to be really, really helpful there. So we now have a minus 4, because 3 goes into 12 4 times, then the parentheses, and we'll leave the x minus 1 in there. And we have our equals, and 12 times 2 is 24. So the blue is just showing you what's changed, the introduction of the parentheses and the reduction of the bottom with the LCD. No more fractions, and that is our goal. We are goal-oriented in here. That is a very important idea, that whenever we do something, we're always trying to accomplish something else. And that something else doesn't always show up immediately, but it should eventually. No more fractions, much easier. So now we just distribute. Remember I said that step 1 can end up happening at any point in time. It's not necessarily do them in these 4 orders, these 4 steps in this order. It's, hey, these things can happen. They might happen in that order, they might not. It might be easiest to tackle in that order, but sometimes 1 or 2 of the steps just shows up. So distributing the 3. So now we're over here. We're coming from here all the way to here. So that's going to give us 3x plus 6. That color's fine. Then minus 4x. Now this minus 4 is being distributed to the x and the minus 1. It's not just the 4 that's being distributed, it's the negative as well. So negative 4 times positive x was this negative 4x. But this negative 4 times this negative 1 is a plus 4. And this right here is where people make their mistakes 9 out of 10 times. Guess what? Your teacher's been there. He's done that. I don't usually do it, but I've definitely made that mistake, even as a teacher, admittedly. I've done it once or twice. It's what happens when we rush. So please watch out for that, because that one little sign error, if you have this as a -4 instead of a +4, everything else is wrong. Your answer is now wrong. My math lab doesn't give you partial credit. So make sure you're being careful. All right, so then the equals 24, that didn't change. Again, let's just go over here to kind of compress space for this problem. Now we can combine like terms. So this was distribute. This would be combine like terms, CLT, combine like terms. So here's our equal sign. So if you have like terms on the same side, you combine them. 3x minus 4x is going to be a -x. Something looks weird. No, that's right, -x. And then 6 plus 4 is going to be a +10, equals our 24. And there's a couple different ways you could solve this. Honestly, there's 10 bajillion different ways you could solve this, but only 2 that get it done quickly. Some people would subtract 10 and then divide by -1. Some people would add x and subtract 24, because there's more than one way to get this job done. I'm going to go with the more traditional way of doing it by moving the 10, then dividing. But again, this is an instance where you could move in a different manner and ultimately get the same answer. So I'm going to subtract 10 on both sides. We're on that third step from above. I don't want to have to keep scrolling back up. So what that gives us is -x is equal to 14. And then we're going to divide, because this negative counts as a -1, -1 times x. So we divide both sides by -1. And what we end up with is x equals -14. Now remember, if you're ever not sure an answer is correct, you can always plug it into the original equation to check it. Sometimes that's easy, sometimes it's not easy. It just depends on the problem. You may end up having to deal with fractions along the way. Hint, wink, nudge for this one. So I generally don't emphasize checking for problems that you don't have to check, but notice those ifs and buts in there. There will be many types of equations throughout this course that we are required to check the solutions in one way or another. I will, of course, teach you those ways. It's not always just plug it in and make sure the left side matches the right side. Sometimes there's shortcuts. Sometimes there's other issues at hand. All right, one more. I don't know that I can fit it there, so let's just play it safe and move it here, D. And this is going to be 0.2x, 0.2x, minus 0.42 is equal to 0.5. I'm only going to do one problem with decimals because most people are a little better handling decimals. They don't always feel it's necessary to clear them, but it is still a great technique. So remember, the official name of decimals is actually decimal fractions. Sounds super geeky. And that's why no one calls them that. They're just decimals. But because decimals are literally fractions, they're just fractions where the denominator would be a 10 or a 100. This would be 2/10, this would be 42/100, this would be 5/10. Yes, some of those could be reduced, but that's just the direct conversions, because the number of decimal places tells you how many zeros you need in the bottom. So you can find an LCD and you can multiply by the LCD and thus get rid of the decimals. So that's step 2 before. It said the LCD for a decimal is, for decimals, is a power of 10. The number of zeros in the LCD is the most decimal places seen in the equation. It's not add up all the decimal places, it's the most that you see out of any particular one. So with that in mind, there are one decimal place, or is one decimal place in this first one, 0.2. There are 2 decimal places in 0.42, and there is 1 decimal place in 0.5, which means that our LCD has to be 100. 2 decimals was the most, so we need 2 zeros. If this was 0.425, the LCD would be 1,000. If this was 0.5291, the LCD would have to be 10,000. If these all had 2 decimal places, the LCD would still be 100. And in fact, I can write them all as 2 decimal places because I can call this 0.20 and I can call this 0.50. That doesn't change the LCD though, because they all still have at most 2 decimal places. So we'll multiply 100 by the 0.2x, then 100 times the 0.42, and then 100 times the 0.5. Now, the great thing about multiplying decimals by powers of 10 is it just moves the decimal right twice. It just moves each decimal right twice. If we were multiplying by 1,000, it would move them right 3 times. So I'm going to show this, but I'm going to erase it in just a second. So 0.2, moving that right twice, and it looks kind of funny because there's an x there, but imagine the x isn't there. That means it's a filler 0, so that's going to be a 20. Moving this one right twice makes it 42. Moving this one right twice makes it 50. So now it's a 20x minus 42 equals 50. There we go. So 20x minus 42 equals 50. Whole numbers, no fractions, no decimals, much easier in the brain. Now we're on step 3. We're adding and subtracting things on both sides to move them. The only thing we need to move is the 42. The opposite of minus is plus, so we add 42 to both sides, which will give us 20x is equal to 92. We're at that 4th step, divide by the number with the x, because that's multiplication. To undo that, we divide. So we divide both sides by 20. Just going to go over here. The 20s cancel on the left, so we get x equals. 92 over 20 does not divide evenly, however, it will reduce. 4 will go into both 92 and 20. 4 will go into 20, what's that, 5 times easily. And then 4 will go into 92, that's 23 times. So 23/5 would be our answer. This is the easiest version of the answer. This is generally what my math lab and what your teacher like because it's the least work. Sure, you can convert them and you could say, all right, well, that's 4 3/5 as a mixed number, or you could say it's 4.6 as a decimal. Those are both correct, but they're more work, and you could convert wrong and then get the answer wrong. And believe me, you're going to be kicking yourself when you had the answer right, did one extra step, and now it's wrong. That's something on a test I can give partial credit for, as I've mentioned, if you mention it to me over email, but I'm not going to do that for homeworks. All right, so at this point, while we have not done a ton of equations, this really is kind of the full breadth of variety in terms of having distributions, fractions, the 2 different types of fraction problems, simpler ones. I mean, you could have a problem with 10 or 12 different distributions to have to do, but we don't really focus too much on linear equations in here. They're kind of boring. We've already studied them extensively in Algebra 1, Algebra 2, whatever previous algebra classes you've done. But that doesn't mean we're done studying them completely, because so far, everything that we've done has had one and exactly one solution out of these 4 problems. And if I'd given you 100 examples, I'm making up numbers there, 100, I was having fun. If I gave you 1,000 examples, they all would have had one solution so far. But that's not always the case. It's not always the case with the real world. It's not always the case in math. Sometimes in the real world, there's more than one solution. Sometimes in the real world, there's 40 solutions. Sometimes in the real world, there's infinitely many solutions. Let's say you have $40,000 worth of bills over an entire year. How do you handle that? Well, you get a job making $40,000 or more. The only solution isn't to make exactly $40,000. You could make $40,001. You could make $41,000. You could make $52,017. You could make $1 million. I could literally just keep naming numbers all day long as they were bigger than 40,000. That's infinite solutions. So getting into that idea, there's 3 ways solutions can be classified, or equations can be classified. They can be conditional. Myself just one more line. There we go. Conditional means that a solution is found. It is a condition in which to solve the solution, that x be this specific number, or one of a few specific numbers. An identity means that both sides of the equations match at some point. The left side is exactly the same thing as the right side. You might say, well, isn't that the point of an equation? Yeah, when all the numbers are plugged in, you want them to both be 8s or 12s or negative 40s or whatever, but before you plug them in, they're not going to look the same. And then finally, we have inconsistent. Inconsistent. There we go. I've been spelling that word wrong for a while. That's okay. And this means that a false statement is found at some point. Just do this. There we go. That's what I want. Identities. Infinitely many solutions. Another way of saying that is a curly bracket and then all real numbers. Another way of saying that is a double-backed R that I have to draw. That's generally not going to be an option in my math lab, but if you go on to advanced calculus and other things like that, you might see that symbol. It's known as all real numbers. So the curly bracket and that blue double-back R literally mean the same thing. It means every single number you can imagine that's real is a solution. And you might be thinking, well, every single number I can imagine is real. Maybe. Or maybe you've heard of the imaginary numbers. So we're not including imaginary numbers when we make this statement, but we haven't talked about those together yet. So let's hold off on that idea. Inconsistence. No solution. Which sometimes is seen as a curly bracket. Give some space because I got to draw this. And then it would be a 0 with a line through it like that. That's called the empty set or the null set. It means nothing. Whatever, I'll delete the S. That was weird. So identities, these are the ones where they will match at some point. So you might have x plus 8 on the left and x plus 8 on the right. Inconsistent means a false statement is found. False means you have a lie. You have something like 3 equals 9. That's a lie. 3 is not 9. Conditional are everything that we've dealt with thus far, where you get down to x equals 23 over 5, or x equals negative 14, or x equals negative 4/13, et cetera, et cetera. So these are the 3 types of equations we can have: conditionals, identities, and inconsistents. Identities means everything is a solution, essentially. Inconsistence means nothing is a solution. So identities means that you get a true statement. Inconsistent means false. False is the opposite of true. Identities have everything as a solution. Inconsistents have nothing. Everything is the opposite of nothing. So let's try this out. Example 2, solve. Black. 2a, we got 4x plus 5 equals 4x plus 5, but with a parentheses. Now this looks like something we would have seen the very first example for A. It's very, very simple. There's not a lot going on. There's no fractions or decimals, so that's awesome. First step, distribute or combine like terms. Well, there's a distribution we can do. We can give that 4 to both of those. So let's do that. So we'll get 4x plus 5 is equal to 4x not plus 5 plus 20. Now at this point, this is where some of you might start to already see an issue, the fact that we have just as many x's on both sides. But let's assume that you're not seeing that, or let's talk for those who don't see that issue. And let's say, all right, well now this is where we'd start moving things from side to side. Now you might go ahead and try to move the 5 or the 20, and that's okay, but you're not going to see me do it. And again, it would have been okay if somebody subtracts 5 or 20 on both sides. But what leads to the point of this problem is not the moving of the constants, but the moving of the variables. If I try to move either of these, the one on the left or the one on the right, they're both positive, so you'd subtract. No matter which one I try to move, I'm going to end up subtracting 4x on both sides because they're the same number. 4x minus 4x cancels, so the left side is just a 5. On the right side, 4x minus 4x cancels. Now what some people will do is they'll go, uh-oh, all my x's disappeared. That's not supposed to happen. Okay, it usually doesn't happen, but it can happen. So some people will try and fudge this and they'll just put an x here, and that's very, very wrong. If 4x minus 4x cancel on the left, they definitely cancel on the right. So the right side is just 20. All of the x's are gone. This is when a yellow flag should be going up in your head. If you do any math and all the variables disappear in an equation, assuming you've done everything correct up to this point, that means it's one of these two new scenarios. It's either everything or it's nothing. So the question is, do you have a true or false statement? 5 equals 20. Lies, slander. That's false. False statements means that you have no solution. False means it's inconsistent. Inconsistent means no solution. So you can say it's inconsistent. I'm going to abbreviate. You can say there's no solution. Again, abbreviating. You can use the symbol for no solution. That's the Greek letter phi or phi, depending on your pronunciation. But those are the different ways you can answer this, and my math lab can ask you any of those ways. It's inconsistent because there are equally as many variables on both sides at some point, and when you get rid of them, the numbers do not balance out. Imagine that you've got a science teacher who puts a balancing scale in front of you and says that this thing is even, but when they hand it to you, it's not actually even. The left side is dropped way further down than the right side. So you were lied to begin with. This is an impossible scenario, which means there's no solution. Let's do a very, very similar example. 4x plus 20 equals 4 parentheses x plus 5. So this looks tongue-tied there. This looks almost identical to the last problem we just did. 4x plus 5, 4x plus 5. The only difference is the left side originally had a 5 here, and now it's got a 20. Well, let's see what that does to the problem itself. So let's still distribute on the right, the 4 to the x and the 5. So what we get is 4x plus 20 on the left and equals 4x plus 20 on the right. Some of you may already have a conclusion about this being an identity because both sides match, but some students really like to see the x's disappear, spoiler, before they start making those true and false identity inconsistent conclusions. So it's my personal opinion that you should probably be doing this next step, but I know maybe 1 or 2 or 3 of you can make the conclusion now, and if you can, that's fine. Remember, we all work at different paces. We all should still be showing work, but the work that we show could be a little different in detail. So again, it's not the moving of the 20s. You could certainly subtract 20 on both sides and they just cancel, but that's not going to tell us anything. It's the moving of the 4x's via subtraction again and then canceling again that really tells us something. It doesn't matter what these two numbers are. If it said 5 equals 5, 10 equals 10, 1 equals 1, 0 equals 0. So if you try and subtract 20 on both sides as well, this would say 0 equals 0. It doesn't matter what these two numbers are. It matters that the x's have disappeared and that they match. So this isn't false. It's true. True statements means that this equation is balanced even without the x's. You can get rid of them and it's balanced, which means the variable is, what's the word I'm looking for? It doesn't cause a dependence. So there is no limiting to the solutions. No matter what you plug in for x here, you can make the left and the right side match. Try plugging in x equals 0. You'll get 20 on the left and 20 on the right. Try plugging in x equals 1. You'll get 24 on the left and 24 on the right. Try plugging in x equals 10,019.73 and you'll get the same number on the left and right as long as you plug it in correctly. So since this is true, the opposite of false, false means no solution, true means everything's a solution. So this is an identity, and it means there are infinitely many solutions. It means that x is equal to all real numbers. And again, there's like 10 different ways to say this. You can use the double back R. You can use interval notation. You can say that the solution is negative infinity to infinity. That would be all real numbers in interval notation. The interval notation for the left one is just not girly brackets. Now I've got Arnold Schwarzenegger in my head saying girly. Curly brackets. So 2 curly brackets with nothing in between them. That's another way of saying no solution because it's empty, the empty set, the null set. Null means nothing as well. All right. There is no C. Next up, we go to rational equations. I do want to point out at least that these 2 problems, this is not something we're going to deal with a lot throughout the semester. I can really only think of like one other case where we're going to see this in the future, but it is a very important linear algebra concept to understand because you can come across linear equations at any point for any reason throughout the math in your years. Just because we're studying the specific topics of pre-calculus and prepping for calculus, these no solutions, every solutions can pop up in calculus. The idea of all or nothing can pop up anywhere, not just related to this scenario. All right, so the last primary topic of 1.2 is on what we call rational equations. And I'll remind you once again that this is all supposed to be reviewed technically. If this is something that you've never seen before, that's a little scary, and you're going to need to put extra time and effort into this. So rational equations, going straight to the recipe, just like we did with linear equations. So 4 steps to solve rational equations. First step, it keeps doing this to me. I wish it wouldn't. It's like I'm trying to write a story. The first step is to factor denominators. Notice I'm being very blatant about denominators. With us, you really don't have to worry about factoring the numerators, but I will mention in the real world of mathematics, if you have a career in this, there's a chance that you got to factor the numerators, but it's pretty rare. Why are we factoring denominators? Because the word rational, remember the word rational means fraction. You've got to remember that all semester long. We're going to be studying them on and off. Rational means fraction. Rational means fraction. What does rational mean? That's right, fraction. So we already dealt with solving fractional equations earlier, believe it or not. Hey, if there's an equation with fractions, multiply all terms by the LCD. So this next thing I'm about to write is literally the same thing as that. I might just phrase it slightly different. Rational means fraction. They're just uglier fractions. They're fractions with variables all over the place, top and or bottom. So we want to factor the denominators because that's going to help us identify the LCD. So identify the LCD. And then multiply all terms, rationals, clear all denominators. So steps 1 and 2 are the same goal, Come on, ignore. What happened to ignore once? Whatever. Again, these two steps in combination are the same goal as step 2 from the linear equations. We have fractions. We don't want fractions. With equations, we can get rid of them. So that's what this is doing. The reason we have to factor these denominators is so that we can actually find the LCD. If you have denominators like x squared plus 5x plus 2 and x squared plus 6x minus 9, you can't say the LCD is just those two things multiplied because they may have some overlapping factors. So once step 2 is done, then I'm just going to keep this as one word, solve. Solve could be all 4 steps of what was previously done. You could have distributions to do. You could have like terms. You need to move things from side to side. You need to divide by the coefficient of x in that very last step. So this is a very loaded word. Kind of like the word factor is very loaded because there's just dozens of techniques in that word. Then there's a 4th step. After solving, we're not done. And I already kind of alluded to this earlier because you must check the solution. You must check the solution. In fact, I'm going to throw in the word must in here because maybe that'll help. Because half my students never want to check the solution. But guess what? If you got an answer right on a test in my math lab that involved this, and you didn't check your solution, if I look over your work and you didn't check it, I can go back and take points from you for not following protocol. Because without checking, you can't guarantee that it actually works or not. You can get these things that are known as extraneous solutions. It looks like it works, but when you actually try it out, it fails. I mean, that just sounds like the real world. We have a lot of things in the real world that sound like a good idea, but when we actually apply them, it doesn't quite work very often. And I'm not going to get into the kind of political ideas that are circling my head right now because I'll go off on a tangent, and we don't need that. So the checking of the solution, sure, you can take the solution, plug it into all the variables, and see if the left side matches the right side. Trust me, that sucks. With these types of problems, it's going to be very heavy in terms of a workload. The numbers are going to be more complicated almost always. You don't want to do it that way. So instead of just plugging it in and see if the sides match, what you should do is the solution makes the LCD equal to 0, throw it out. Garbage. It's extraneous. It's a solution that seems to work but doesn't really. Oh, my brain wants to scream out some of these things and I'm not gonna. Again, because it's not math, it's politics. So is this the only way to check the solution? No. Is this the way I'm going to emphasize? Yes. If you have another way that you use, go for it. One other way would be to initially set the LCD equal to 0 to tell you what the restrictions of the domain are. And that's an angle we'll approach from a little bit later in the semester, where we're kind of finding the domain, but we'll save that for another chapter. But that is something that you see in the prereq material, talking about the restrictions or domain of a rational. Okay, so example 3. Oops, wrong color. It's so weird how sometimes the undo does not undo the draw until 3 steps later. And you know what? I didn't even want to draw it that way. I'll do it this way. Solve. Solve y1 equals y2, where y1 is equal to 3 over x plus 6 plus 1 over x minus 2. And then y2 is equal to 4 over x squared plus 4x minus 12. So this looks like a different setup than what I've done so far, and I will admit the only reason I do this setup is because you'll see it in your homework for a few questions, and there's a strong chance you'll have one on your first test that'll have this setup. This is kind of set up like a system of equations where we've got y equals this and y equals that, and we're trying to solve that system of equations. That's the relationship here, but don't overthink this. I don't know what it is about this problem, but students are constantly overthinking. What are you not going to do? You're not going to overthink this. You're not trying to solve this. You're not trying to solve this. You're setting whatever represents y1 equal to whatever represents y2. What represents y1? This thing. What represents y2? This thing. So it's these two blue circles that we're setting equal to each other. So here's the y1, 3 over x plus 6 plus 1 over x minus 2 equals, and then here's the y2, 4 over x squared plus 4x minus 12. Okay. So this is the equation we're really after. You could have seen many problems written this way instead of the y1 equals y2 jazz, but again, it's something that my math lab likes to do. It's something that you'll see on the test because of that, and I'm straight out saying that you will see a problem like this on your first test, where you have a y1, a y2, and you got to set them equal to each other. There's nothing crazy in that aspect. But if you don't do that, you can't do the rest. So we're on step 1, factor the denominators. Now, I will admit this one problem I'm going to do before actually giving my quick factoring review, but I can at least say that it is technically review material, and I gave you access to that, so if you were rusty on factoring, that's something you should have studied this past week. But in section, I want to say 1.4 or 1.5, one of those two, I will give a quick summary of all my factoring techniques, I promise. But for now, because this has a leading coefficient of 1, this trinomial, I'm kind of jumping the gun. X plus 6 you can't factor, x minus 2 you can't factor. There's no squares, there's no GCFs, none of that stuff. So we're going to leave those alone. Oh, I'm going to run out of room. That's all right, I'll just go to the next page. Let's do it this way. So going over here, so that's 3 over x plus 6 plus 1 over x minus 2. Again, not doing anything to either of those because they can't be factored. But the x squared plus 4x minus 12, the idea is that you want to take the minus 12, you're going to take this number, which is a minus 12, and you're going to write all the numbers that can multiply to it. 1 times 12, what happened to my 1? 1 times 12, 2 times 6, or 3 times 4. So those are all what we call factor pairs, pairs of numbers that multiply to 12. But you got to make sure you find the pair that will subtract to 4. How do I know subtract? Because this was a minus. If this was a plus, then I'd be trying to add to 4. That's why I wrote this sign, because this tells me whether to add or subtract the pairs. So I'm trying to make a 4. Well, 12 minus 1 is 11. 3 minus 4 is 1. So 2 and 6 are the choice. You're not only just using the 2 and 6, though, you have to give them signs. You have to give the 2 and 6 signs to appropriately add to a positive 4. If you do positive 2 and negative 6, that would add to a negative 4. If you make them both negative, that would make a negative 8. If you make them both positive, they'd both be positive 8. They also wouldn't multiply to a negative 12, but that's another issue altogether. So we got to go positive 6 and negative 2. Positive 6 and negative 2. So that says that the factored form would be x minus 2 times x plus 6. This is called the shortcut method. When there's no coefficient written here, when it's a 1, it just has x's in the first spots and then numbers in the second spot, and the numbers are found as I just said. There are many other ways to get this factoring job done. Some of you might use the box method. Some of you might use what I think is called the push and pull method. I don't care how you get your factoring done. I will teach you the ways that I teach. I'm not going to teach you the ways that I don't teach. You'll need to go to the internet or someone else for those. But again, I don't care how you're factoring. I just care that you have a factoring method that works for you, or all the factoring methods. So this right side is going to be 4 over x minus 2 times x plus 6. And if you don't trust your factoring, you can FOIL that out and you should get the original trinomial, and you will. X times x is x squared. For the outer, x times 6 is a plus 6x. For the inner, negative 2 times x is negative 2x. 6x minus 2x is 4x. And for the last, negative 2 times positive 6 is negative 12. If you'd made these both negative or positive, then the product would be a positive 12. Remember how I said that you have to have a lot of skills inside of you with your signed arithmetic because it's always going to come up throughout the semester. Your calculator is not really going to help you that much. This is what I'm referring to. It's factoring. If you're using a calculator for all your factoring, it's going to take you 6 times as long to do them. These are skills you need to have in you, not in your calculator. All right, so next page. Identify the LCD, multiply all terms by it to clear your denominators. So we have denominators of x plus 6, x minus 2, and x plus 6 times x minus 2. And an LCD for these works the same way as numbers, believe it or not. So when we found an LCD of 12, one of the denominators was 3, one of them was 4. And 3 times 4, those are all the different factors, is 12. Remember, you have denominators of 6 and 4. Well, 6 is 2 times 3, 4 is 2 times 2, so your LCD has to be 2 times 2 times 3. All the different factors, but if there's multiples of any, you have to take the multiples. So we have x plus 6s and we have x minus 2s, but there's only one of them in each fraction. You might say, no, there's 2 of each of these. Notice I said there's only 1 in each fraction, so we don't need multiples of any of them. So what we have is, oops, an LCD. What in the world is happening? Our LCD is x plus 6 times x minus 2. Again, the product of the different factors from the denominators. If this was an x plus 6 squared, I'm saying if, then this would need to be an x plus 6 squared because there would now be multiples of them in a single fraction. But it's not, so it's not. So what we get, the LCD multiplies by the 3, the 1, and the 4. It goes into the tops of everything, or if it's a whole number, just the whole number. So blue, here's my 3 over x plus 6. And we're going to give the 3, the x plus 6, and the x minus 2. This is exactly what we were doing before when we multiplied those 12s. We were multiplying to the tops. I was putting them in front of the numbers before, but because these are variables, it makes sense to do them after. Plus 1 over x minus 2 times x plus 6 and x minus 2 equals 4 over x minus 2 x plus 6. And then it gets the x plus 6, x minus 2. This is not a multiply by what's missing, it's a multiply by everything. Okay, so why did we do this? Remember, well, hold on, not remember, but this looks a lot uglier, but remember the goal was to eliminate the fractions. And that's exactly what we should see happen. Can I just quickly copy paste this? Let me see. Wonderful. Well, that didn't work perfectly. There we go. So here's what's going to cancel. You got an x plus 6, top and bottom, gone. You got an x minus 2, top and bottom, gone. Then in this fraction, you got the x plus 6s, and you have the x minus 2s, so they're all gone. I'll give you a second to catch up there, because I quickly copy-pasted something, and you have to write it. Why did we do this? To cancel the fractions. Is that what happened? Yes. Awesome. No more denominators, so this is just 3 times x minus 2 plus 1 times x plus 6. No, you don't need to write that 1, but I'm trying to be meticulous. Equals, and that's just a 4. A lot of people think that ugly denominator on the right side meant this was going to look terrible afterwards, but in fact, it actually makes it simpler. It's kind of cool. Okay, so now we just distribute combined like terms. Like I said, that first step can pop up later, and as it has just done. So we're going to distribute this. 3 times x is 3x. 3 times -2 is -6. Distributing 1 does nothing, so that's plus x plus 6. As long as that's not a -1, watch out distributing your minuses, and that's 4. We will then combine like terms. The 3x plus the x is going to give us a 4x. The -6 plus the 6 actually cancel. That's kind of cool. And then the right side is still just a 4. Again, the 6 is canceled if you didn't see that. The 3x plus, there's an imaginary little 1 there still. 3 plus 1 is 4. So we get 4x equals 4. Very simple last step. Divide both sides by +4. And we get that x is equal to 1. And some of you might be doing this. Notice I'm saying some of you might be doing this. I will erase this. Some of you might be doing this and saying they're done. Yay, happy face, done. Nope, very wrong. We're not done. We should not have boxed that up. Because if you pay attention to the instructions, if you're writing these down like a good student should, you must, under all conditions, check the solution of these fractional equations, these rationals. Now you might say, Mr. Beckner, we had 2 fraction equations earlier that we didn't check, and you said that was fine. Look at the difference of them. This was a fractional equation you don't have to check. Where are the variables? In the tops. Look at C. Fractions, but the variables are in the tops. Look at the one we just solved. The variables were in the top as well, but they were in the bottom, and that's the problem. That's what gives it a true sense of being rational, a more complicated fraction. When you have variables in the denominator, there is a number you are not allowed to divide by, unless you're a super fancy quantum computer, and that's 0. 0 is the one and only number in the world we cannot divide by. It causes things to go very, very wrong. So it leads to what we call undefined answers. So if a solution happens to make a denominator 0, that means the solution makes us divide by 0, and it makes, I always like to have fun and say it makes the world explode. It's just a joke, but it makes things go wrong. So we have to make sure that this doesn't happen, because it's possible. It's possible that we solve this and that solution could make the denominator 0. And the reason is because of this step where we clear out the denominators. By doing this, we're kind of hiding something. We're putting something under a veil, if you will. So we must, under all conditions, check this solution. And I said, sure, you can go back to the original equation, see if it makes the left and right side match. You probably get the idea that it's going to be ugly. I said the easier way is to see if it makes the LCD 0, and if it does, then toss it out. Because if it makes the LCD 0, the LCD has all of the different denominators built into it. So if it makes the LCD 0, it means it made at least one of the denominators 0, so it doesn't work, throw it out. So let's try that out. As a reminder, what was our LCD? It was x minus 2 times x plus 6. So we're going to put x equals 1 into that. So we plug x equals 1 in. So our LCD would become 1 minus 2 in parentheses times 1 plus 6 in parentheses, which is -1 times 7, which is 7. And 7 is not 0, so that means it does work. If this number had been 0, it would have failed. It can be any number in the world except 0. Because it's not 0, then it works. So x equals 1 is the solution. Now don't worry if you're wondering what it'll look like when it is 0. Spoilers for the next problem. So quickly discussing again, remember your 4 steps. We factored, we found the LCD, we multiplied all parts by it, either top or if it's a whole, the whole, not the bottoms, because we're reducing the bottoms. No more fractions. Clean up, clean up, clean up, solve, check. This is the easiest way to check, to make sure that the solution does not make the LCD equivalent to 0. All right, one more, and we'll call it the section, not the day, just the section. 5 over x plus 2 plus 3 over x minus 2 equals 12 over x squared minus 4. First step, factor. X plus 2 you can't factor, x minus 2 you can't factor, x squared minus 4 you can. So this is going to become 5 over x plus 2 plus 3 over x minus 2 equals 12 over, this is what we call a difference of squares, and again, I will give a little more quickly of a formal factoring review, if not the next class, the one after. But this is a formula, a squared minus b squared is equal to a plus b times a minus b. That's called a difference of squares. I'm abbreviating, difference of squares. So if you have x and squared it, you'd get x squared. If you had 2 and squared it, you'd get 4. So that's the a and the b. So that's supposed to be x plus 2 times x minus 2. Notice that there's a lot of coincidences happening here. It's not always that coincidental, but very often when you have to factor something, one of its factors is probably elsewhere in this type of equation. So with denominators of x plus 2 and x minus 2, none of them repeated in any single fraction. That means our LCD is x plus 2 times x minus 2. That's what we'll multiply the 5, the 3, and the 12 by. Some room. Five, x plus 2, x minus 2, the 3, and the 12. Even if that 12 did not have the bottom part, even if this was not here originally, the 12 would still get the x plus 2 and x minus 2. It doesn't matter that it's whole. So then we reduce. So I was able to do this. Now you in your own notes, you don't have to do this little copy paste thing I'm doing. Nope. Which is really fun to get set up. Why didn't it take the, let's try that again. Darn it. I'm taking more time to do this than if I had just written it out myself. Forget it. So now we have 5, x plus 2, x minus 2. I try to save time and it wastes time. Sorry about that. Then plus the 3, x plus 2, x minus 2, over x minus 2 equals 12, x plus 2, x minus 2, over x plus 2, x minus 2, and then we cancel any common factors top and bottom. The x plus 2s are gone from the first, the x minus 2s from the second, and on that right side, everything except for the 12 is going to be gone. So now we have 5 parentheses x minus 2 plus 3 parentheses x plus 2 equals 12. And from here, this looks very similar to the last one we did. So the steps will follow through very similarly. We're going to distribute, combine like terms, move, and then divide. And again, the point is not to memorize those 4 steps blindly. It's to understand when to apply them. When you see this, do that, that kind of thing. Action, reaction. So we'll distribute because we see things to distribute. So 5x minus 10 plus 3x plus 6, and then equals our 12. We now have like terms on the same side of the equals, so we're going to combine those. The 5x plus the 3x should give us an 8x The negative 10 plus the 6 should give us a negative 4. The right-hand side will stay the same as an equals 12. And then because we don't have any more like terms or distributions or fractions, we're ready to start moving things. So it's going to be easiest to add the 4 to both sides, giving us 8x equals 16. Then we'll divide both sides by 8 to give us x is equal to 2. And some of you are going to box it up and ship it out and happy faces, yay. No, don't box it up. You're not done. Now, last time you were like, well, it worked, so why do I have to actually check it? Hint, wink, nudge. You must check these. As a reminder, our LCD was x plus 2 times x minus 2. This is what we're plugging our solution of 2 into. So we get, our LCD is now 2 plus 2 times 2 minus 2, which is 4 times 0, which is 0. Uh-oh. That's the one and only one number it can't be. Because the solution makes the LCD 0, that means it makes at least one of the denominators 0, which means we're dividing by 0, which means the world, as we jokingly say, blows up because of that. So no, the x equals 2 does not work. It fails. It was the only solution, so that means there is no solution. Or that circle with a line through it. Now, what if in the solution process you found 2 solutions? What if one of them works but not the other? Do you say no solution? Well, no. If you have 2 potential solutions and one works, that's not no solution. That means there's a solution. So be careful with that. Now, you could have a situation where it looks like there's 2 solutions, but both of them fail. It used to be my favorite thing to do for college algebra students, just to really make sure they're checking, and then half of them wouldn't. Now, if you had 2 solutions and both fail, then you can go back to saying no solution. But you can have multiple solutions and some work. You can have multiple solutions and they all work. You can have multiple solutions and none of them work. And sorry if you hear my dog barking right now. And yes, he's barking, not barking. Give me a second because he's distracting. All right. Now, that is the end of 1.2. So 1.2 due, today's the 31st, right? So I've already got it set up in my math lab. It'll be due on the 6th. So Monday, September 6th. And as I said, I will not always 100% of the time make these little notes. I will mention a section is complete, and then you are supposed to know, based on what we discussed day 1 of class, that homework is due 1 week later, and then that's by 11:59 p.m. So I always give you exactly 1 week from finishing a lecture. The only exception might be like the last day of class. You might have a homework due, you know, the last day of class from the previous day of class. Seen a couple chats. Oh, all the borks. I love it. I love y'all so much. All right, so that's 1.2. Now I'm going to pause my screen for just a second because I want to find a file. Where's my 1.3? Here we go. All right. 1.3, models and applications. So I've got some stuff that's kind of pre-written. I pre-type something sometimes. Sometimes I like doing it on the fly. I'm weird. I don't like prepping everything, and I don't like doing everything on the fly. I like a little mix and match. especially when they're application problems. I'd rather have them go ahead and typed ahead of time when possible, as you'll see later. So models and applications, everybody's favorite thing in math, it means word problems. Here's the thing though, life is literally a word problem. It doesn't have to be mathematical in nature, but it is. So just a couple quick tips and tricks, nothing super extensive. Again, you need to do a little more research on your own if you're extremely rusty with word problems in the process. But these kind of 4 or 5 steps are very, very helpful and generally how I would do things. Read the question, then read it again. Don't read a sentence and start trying to set things up because the next sentence might say disregard the first sentence. Or maybe the problem has just got 50, 60 different numbers in there. And really there's only one thing that you actually need out of it. You're just overloaded with extra information. I mean, that's just society now, right? TMI, too much information. So read the question, read it again. If you got a highlighter and you're using physical things, or if you've got a Word file, you can highlight with Word. Highlight the things that you believe are important. Then go through and identify what you know and what you don't know. And generally the things that you don't know, you're going to call them variables. X, Y, Z. Maybe you want to just use X in different ways. Maybe you want to use X and Y. I mean, it's up to you how you're doing things. I'm going to give the simplest approach in my examples, but that's not to say that some of you might not know, or might not be more successful with a more complicated approach. Then, like our mommies and daddies tell us, use your words. Write out an equation in words. Don't just go straight to x times 3y minus z equals blah, blah, blah. Write it out in words. I can't tell you how many times this has saved myself, my students, anybody really. Especially with the first problem, the first example we're going to do together, which we might have enough time to finish. I'm kind of thinking on whether or not 9 minutes is enough, but we'll try. Once you have your equation in words, you want to make sure you place your knowns and unknowns into the equation. So if you have a word that was one of your unknowns, then you throw your X in. If you have something that was all numbers, you put the numbers in. Once you have your equation in numbers and X's, then you solve it. At this point, they should all be on the level of what we've seen in the last section. And I'll admit, I believe all of the examples in 1.3 are linear equations, not rational equations. So they should be of the easier type. So you solve them. And then I say to check them, but a lot of the times it's more about just making sense. Let me give you an example of when an answer would not make sense. I have a problem and I'm supposed to be finding the length and width of a rectangle. And when I get my solution, I find that the width of the rectangle is supposed to be -3 feet. That doesn't make sense. You cannot have geometric shapes with negative dimensions. So that's an idea of just, it's not actually going through and checking mathematically. It's just saying, hey, that answer makes no sense. It's probably wrong. I must have made a mistake somewhere, or there's a lie in the math, kind of like with those rational equations. So sometimes it's as easy as just making sense of it. Sometimes you may actually have to do some arithmetic to check it. It'll vary, but usually it's about making sense for us. All right. I don't see us finishing this problem in 5 minutes. So you see the problem already. Maybe what would be a good idea for you to try out is to try this on your own. So you've seen it on your screen, it'll be on the replay. Maybe you can get the answer before next class, but in next class, we'll have this up, we will set it up, we'll do all the things that I've said to do, and we'll get our answers. But there's your problem. I'm not even going to read it out loud since, like I said, it's only 4 minutes left of class, which will not give us enough time to solve it. So we'll leave it there. We didn't really get too heavy into 1.3, just kind of introducing it, leaving us with bated breath, waiting for next class. Super anticipated, I'm sure. So we will call it a day. If you have any questions, you got another 60 seconds roughly to ask. Besides that, you know that your 1.2 homework is due in 1 week, September 6th. You know that you have that prereq assignment that you can still work on to get those 5 bonus points for test 1, which I believe is an amazing opportunity, and I highly encourage you to do that, even if you feel awesome with the material anyways. And those of you who feel pretty confident with the material, you still might find a question or two that's, you know, a little bit out of your reach, or you just have to shake some rust off of. I mean, I always like to say I'm pretty good at math, but if I don't do a subject for 5 years and come back to it, trust me, I'm shaking off some rust. I can't tell you how many mathematical formulas I've forgotten and then remembered because I came back to it. That's just how our brains work. If you don't use it, you lose it. All right, so we'll have a good day from there. Take it easy. If you have any questions, you're free to shoot me an email. We'll see you on Wednesday, ready to go right into this example. If someone asked if we finish, Monday is the 7th, isn't it? I'm sorry. So I think it should say the 7th in my math lab. That should be correct. I just have the wrong date up there earlier. So thank you for mentioning that. If you finish 1.3, and I did say Wednesday. I thought I said Wednesday. Anyways, if you finish 1.3 tomorrow, will the homework be due next week? Yes. That was your own asterisk. You weren't correcting me. If we finish 1.3 in class on Wednesday, which is likely, then yes, that homework would be due a week later, which would which would be the 9th. So 1.3's homework is most likely due on the 9th. Good question. All right, we'll leave it on there. You're welcome, and have a good day, everyone. Take care.